Okay. So, are there any questions before I start? So tomorrow at this time we'll have a quiz. Yeah. So there won't be any class. I'll upload the question paper, and you'll have to submit the. You'll have to turn in the answers in Google Classroom. So if you have, but I'll be online. So if you have any difficulty, you can. I'll be online on Zoom. So if you have any difficulty, you can ask me questions on the Zoom, the Zoom meeting. Okay, and I hope so. I've given time till 1, but I mean there isn't enough questions, so I hope you'll be done by 12:30. But I'll be online till 12:30, so you can ask me questions if you have any about the quiz, or how you or if you have difficulty submitting it on Google Classroom, you can ask questions related to that as well. Okay, and in worst case scenario, if you aren't able to do it, and we aren't able to resolve it over the Zoom meeting, then you can just email me your answers, uh, and I'll grade it there. So the quiz will be based on whatever we have covered till now. So today's lecture is not included in tomorrow's quiz. Yeah. So whatever we covered till Tuesday is in there. No, there won't be any class tomorrow. So I'll be online just to assist you in uploading and stuff, but and you can be online as well on Zoom, but there won't be any class tomorrow. Okay. Any other question? So if you have any issues with the quiz during the quiz, I suggest you better be online and explain it to me. Yeah. So between 11 to 12:30, as usual, I'll be online tomorrow. So you can tell me if you have any. Any other questions? So I had emailed you about the weightage of various things. So that the guidelines from the center hasn't from the Dean of Studies hasn't come yet, a concrete guideline. So there has been some speculation and some suggestions, but the concrete guideline hasn't come. So that's so the breakup which I had emailed you yesterday, that's subject to change. Yeah. So it may change, but as soon as I know what the guidelines are, I'll make the changes accordingly. So if the dean thinks that weightage for final has to be a little more, then we'll make the changes accordingly. Okay. So as of now, if the suggestion or the guidelines from the dean, if this model fits into the guidelines of the dean, then I'll leave it as it is. Otherwise, I'll make changes accordingly. Okay. Okay, so let's get started. So last time we talked about prime ideals and maximal ideals, and a little bit about maximal ideals. That is mostly prime ideals. So let's just recall. So from now onwards, we are sort of working on a commutative ring with unity. So if I forget to mention sometime, you can just assume that R is a commutative ring with unity. Unless otherwise stated, this is the bottom line. Yeah, this is the assumption. So recall that I contained in R is a prime ideal if I is a proper ideal and AB belongs to I, implies A is in I or B is in I. And then we saw, so this is the definition, and then we saw that I contained in R is a prime ideal if and only if R mod I is an integral domain. Yeah, so So one can prove it directly, or you can, which is what we did, or we saw this result that zero ideal is a prime ideal in a ring if and only if the ring is integral domain. So you can use that result as well. By comparing what are the ideals in R mod I. Yeah, so you can use that result and this comparison result which we did between ideals in R containing I. So we know that there is a bijection between ideals in R containing I and ideals of R mod I, and this bijection is explicit. Yeah, so you know how to go from one side to the other. The map is explicit, which is given by the quotient map. Yeah, Q. So then we saw the definition of maximal ideal. So a proper R ideal is said to be maximal if there does not exist any ideal between M and R. Yeah, and that's a restatement of what we did. So another way of saying it is, if I is between M and R, then I is either equal to M or equal to R. Yeah. So there are many ways of thinking about it. So in the same vein, I is said to be a prime ideal in R if I is not equal to R, and you can write it as a negation of this. Yeah, so A and B does not belong to I, then their product cannot belong to I. Yeah, that is what the negation of this, contrapositive of this is. Okay, so this is a observation which we sort of made last time as well in a proof or something, but this is, it's a trivial observation, but it's a useful observation. Yeah. So I, an ideal of R, then I equals R if and only if one belongs to R. Yeah. So this is of course, if I equals R, then everything in R belongs to I. So in particular, 1R belongs to I. And if 1R belongs to I, then any multiple of 1R is belongs to I, and hence whole of R equals I. Yeah, so this is a trivial observation, but it's a useful observation. So whenever you are given an ideal and you want to check whether the ideal is the whole ring or not, then you just have to make sure that one of the ring belongs to I. Yeah, so somehow you have to ensure one belongs to I. Okay, so now, like this number 2, there is an analogous statement for maximal ideals. So let R be a commutative ring, and I be an R ideal. Then I is maximal ideal if and only if R mod I is a field. Yeah. So if you so it's in the same spirit as number 2. Yeah. And somehow this should become. So the proofs are not difficult. So there are 1 or 2 lines, and so people, people think of this statement as inherent. Somehow you should think of it as quite obvious kind of statement. Yeah, eventually it should become second nature. So I'll prove this. So I'll give you. So this is not a difficult statement, but I'll prove it using some. So I'll prove it using the philosophy that you can check it. So last time when I proved the statement, I contained in R a prime ideal if and only if R mod I is an integral domain. I think I did it directly, instead of using the fact that 0 is a prime ideal in R if and only if R is an integral domain. But this time I'm not, so this statement I'm not going to do it directly first. I'll try to use this fact. So similar to integral domain, there is this fact about fields. So R be a commutative ring with unity, then R is a field if and only if ideals in R are 0 and R. The only if and only ideals. Maybe one should put the only ideals in R are 0 and the whole ring. Yeah. So this is something about fields, and then we will use this quotient construction to say that this lemma implies this proposition. So it may seem like I'm using a sequence of arguments, but I'll give you a direct proof as well. So it's not deep result. It's just that there's a philosophy, and one should think of it, think of various things in various philosophies. So it's good to know. So one should be comfortable comparing ideals in R and ideals in R mod I and so on. So that is the reason I'm giving you this proof. So let's see the proof of this lemma. So this I don't know if you have seen this result before, but it's a two-line proof. So for the forward direction. So that means if we assume R is a field, we want to show that the only ideals in R are 0 and R. So let I be an ideal of R, yeah, and assume I is not 0. Then we have to show that I is whole of R. Yeah? So if I is not 0, there exists an element, I is not the 0 ideal, I mean. So 0, maybe I should put here. Yeah. So one should think of it as a set, yeah. Set containing only 0. So if I is not a 0 ideal, then there exists A in I and A not equal to 0. Yeah. Then A is a non-zero element of this ring R, which we have by assumption is a field. Then we can find A inverse such that A inverse times A is 1. Yeah. So we can. So every non-zero element in a field has an inverse. So we have that 1 also belongs to I, which implies by this observation I is equal to R. Okay. So that proves the forward direction. Any questions so far? Okay, no. Okay. Now for the other direction, let A, so now we'll assume that this commutative ring with an unity has only two ideals, 0 and R, and we want to show that R is a field. Yeah, so to show R is a field, we take a non-zero element and show that it's invertible. Yeah? That is the definition of it. So let A belongs to R, A non-zero. Then consider this ideal A times R. So it has to be a non-zero ideal because it contains A. Yeah. So that tells you that A times R is whole ring R because there are only two ideals in this ring R. Yeah? The zero ideal and the whole ring. So if it's not the zero ideal, it must be the whole ring. So that tells you that there exists B in R such that A times B is 1 of R. Yeah, because this is how the any element in the left hand side here looks like. It's A times B for some B in R. And so in particular 1 in R, we can write it as A times B. So that tells you that A has a multiplicative inverse, and hence every non-zero element has an inverse, and hence R is a field. Okay, so that proves this lemma. So field has so this is an equivalent definition of field. So every non-zero is a commutative ring with unity, where every non-zero element is invertible, or it's a commutative ring with unity which contains only two ideals, the zero ideal and the whole ring. Okay. So they both are equivalent definitions of field. Okay, so now let's look at the proof of this proposition that that I is a maximal ideal of R if and only if R mod I is a field. Yeah, so let I contained in R be a so I contained in R is a maximal ideal. This is equivalent to saying that the only ideals in R mod I are the zero ideal and R mod I itself. Yeah, this is clear by the definition of maximal ideals. Right? Since the and comparing the ideals in R mod I with ideals in R containing I. Yeah? So recall that since ideals in R mod I are in bijection with ideals of R containing I, and I being maximal, there are only two such ideals. Yeah, one is I itself, and the other is the whole ring. Maximal ideal means there can't be any ideal between I and R. No? So there are only two ideals which contain I, which is I itself and R, and their image and whose images under Q. So image of I under Q will be the zero ideal here. Right? I goes to I. I go. The image of I here is the zero ideal, 0 plus I. I goes to 0 plus I, and 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 the image of the whole ring will be R mod I. It is projects onto this. Okay. So that tells you that the only ideals are zero ideal of R mod I, and the zero and the whole ring R mod I. Yeah. So this thing in the bracket is supposed to explain this this equivalence. Yeah. So okay. Okay, makes sense. So now by the lemma, since there are only two ideals in R mod I, zero ideal and R mod I, this is equivalent to saying that R mod I is. Yeah. So the proof is just these two lines, assuming the lemma. Okay. Any questions? Okay. Okay. So our corollary to this thing is that so maybe I said I'll give you a different proof of the proposition, but let me not. So one can do. So you can directly prove it as well, but let me not do that. But I'll give a different proof of this corollary, which is what I had written it down. So R a commutative ring with unity, and I contained in R a maximal ideal, then I is a prime ideal. Yeah? So in particular every maximal ideal is a prime ideal. So that I said in the last class as well, and I said we'll see the proof today. So from what we have seen from the proposition, so it's a corollary to the proposition that I is a maximal ideal if and only if R mod I is a field. Yeah. So R a commutative ring with unity and I a maximal ideal, then I is automatically a prime ideal. Yeah, so let's see a proof of this guy, the statement. Yeah. Okay. Okay. So I is a maximal ideal of R. So we will prove that it's a prime ideal. So I is a maximal ideal of R. That tells you that R mod I has to be a field. But we know that fields are in examples of integral domain. In fact, every non-zero element is not just a non-zero device; it's a unit. Yeah. So units are non-zero devices. So R mod I is a field, which implies R mod I is an integral domain. And once R mod I is an integral domain, we know that I is a prime ideal. So this is from the proposition. This is proposition. And this is obvious. Every unit is a non-zero divisor, and every non-zero element in a field is a unit. And this is number 2. Yeah, number 2 in this thing. So I is a prime ideal. So R is a commutative ring with unity. So it seems like we are using this proposition, this lemma, this result number 2, and so on. So it looks like there is a lot of things that goes into it. But this is a more categorical way, or more more big picture way of thinking about it. But there is one can write a direct proof as well. So even the direct proof is not that difficult, and just meaning it has only two or three lines. So I'll give you the direct proof as well. But once the statement becomes second nature, then this is the proof which comes most naturally. Yeah, people don't like thinking in terms of calculation. They more like thinking in terms of concept. So this is like a more conceptual proof, and one can do a calculation-based proof. Yeah. So another proof of the curl. So I mean, it's the same. The argument is essentially the same. If you nail it down, then this is what it comes out. So you want to say that I is a maximal ideal, then it's also a prime ideal. Yeah. So of course I is a maximal ideal means I is a proper ideal. So now let A times B be an element of I for some A, B, and in R. Then we want to show that either A belongs to I or B belongs to I. So you look at this this ideal RA plus I. Yeah, sum of these two ideal. One is the ideal generated by A, and the other is the ideal I given to you. So this sum is an R ideal, and of course it contains I. Yeah, because there's the second term is I. So it contains I. So by maximality of I, that is missing. By maximality of I, RA plus I has to be either equal to I, or RA plus I has to be equal to R. So what does this mean? RA plus I equals to I means this element A, which is in RA plus I, belongs to I. Yeah, so this so we have to show either A belongs to I or B belongs to I. So if the first condition holds, then A belongs to I, and if the second condition holds, we will show B belongs to I. So RA plus I equals R. What does that mean? There exists an element R in R and X in I such that RA plus X equals 1. Yeah, that is what. So you can write any element in R as some element in this ideal plus some element in this ideal. A typical element of this ideal looks like R times A for some element R of A, some element little r of the ring R, and we take some element of I. Yeah, so we have this equality. Now multiply this equation by B. Yeah, so that tells you that RAB plus XB equals B. Yeah, but in RAB, this term RAB belongs to I. Yeah, because AB belongs to I, so any multiple of AB is also in I, and X times B also belongs to I because X belongs to I. Yeah, so both these terms belongs to I, so their sum belongs to I. So that tells us that B belongs to I. Yeah. So that's it. So we have shown that either A belongs to I or B belongs to I. So that's another proof of saying that a maximal ideal is a prime ideal. Yeah. Any questions? Everyone with me? Okay. So there are no questions. So what do we think about the converse? So is every prime ideal maximum? So we know that every maximal ideal is prime. Is every prime ideal maximal? So of course not. So we saw this example that zero ideal in the ring of integers is a prime ideal, but it's not maximal. Yeah. So there are prime ideals which are not maximal. But what about is every non-zero prime ideal of a ring R maximal? What do you think? Yes or no?
I think not necessarily. If we consider z cross z, we will face a problem.
In Z cross Z, what is a prime ideal which is not maximal?
0 cross zp maybe.
0 cross Z. Yeah, so that's so Z cross Z gives you an example. 0 cross Z. But what if yeah, so what if R is an integral domain? So somehow there it wasn't an integral domain. Yeah. So 0 is not even a prime ideal there in Z cross Z. So non-zero prime ideal of a integral domain. Because I want, since I want non-zero excluding some obvious prime ideal. So here 0 cross Z is some sort of obvious prime ideal. So,
Yes, zx x is not.
yeah, so integral domain. So even then it's not true. Yeah. So example is Zx. So Zx is a integral domain, and which prime ideal of Zx is not maximal?
Generated by x.
Generated by x or generated by 2, for instance. So this we have already seen. So I'll just use this example 2, and I'll come to this the other example as well. So example is 2 or x. Yeah. So you look at so for instance 2 we have seen. So um, so 2 is a so you just compute zx mod. So sorry, zx mod the ideal generated by 2. Yeah. So that means 2 zx. Yeah. So as I said, we'll understand this from context what this means. So this we saw is isomorphic to z mod 2. So here 2 means 2z. Yeah. So this we saw last time. So when we go mod this ideal, so 2zx in zx, then what we get is an integral domain but not a field. Yeah, so z mod 2x is an integral domain but it's not a field. Why is it not a field? So if you take a polynomial x, then it can't be a unit, right? X is not a unit there, because if you multiply with any other polynomial, the degree of that polynomial has to be at least 1. Any other non-zero polynomial, the degree has to be at least 1. So you can't get the unit. One bar you can't. So it's not a field, but it is an integral domain. So that tells you that this ideal is prime ideal, but not maximal. Similarly, if you go mod, yes, go ahead.
Can you repeat what you just said? I got lost. My connection was a little slow.
Repeat what?
What you just said.
So if you go mod 2, what you get is z mod 2x. Yeah, you get this ring. If you go mod this ideal generated by 2, and z mod 2x is an integral domain but not a field. So it's integral domain because z mod 2 is a field, and which is an integral domain, and polynomial ring over an integral domain is an integral domain. This is something which we saw. Yeah? So the right hand side is an integral domain, and hence the left hand side, which is isomorphic to this, is also an integral domain. So that tells you that the ideal in below, this ideal generated by 2, that is 2zx. So we are still in the early stages of the class, so let's do this. So this ideal 2zx is also a prime ideal in zx. Yeah, but it's not a maximal ideal because z mod 2 adjoint x is not a field, and this is not a field because x is not invertible. For instance, x is a non-zero element. The polynomial x is a non-zero element of z mod 2x, and it's not invertible, because if you multiply something with x, then the degree of the polynomial is at least 1. Yeah. If you multiply some non-zero number to x, then the degree of the polynomial is at least 1. And I mean, even if you multiply with 0, you get 0, and 0 has undefined degree. You can take it to be degree to be infinity. So the degree of the product of any polynomial with x is at least 1. So it can't be 1. Yeah, you can't get the constant 1, because constant has degree 0. So the right hand side is not a field, so this ideal cannot be a maximal. Okay. Is that clear now? Yeah. Did I lose you again? Okay. Okay, let's hope I didn't lose him again. Okay, so and then x is also a prime ideal, so gx. So x is also a prime ideal. So I mean, one can also try to show this directly as well. Yeah. So maybe I'll try to show this this directly. So x gx is a prime ideal. So what do we have to show? So we have to show that if product of two polynomials belong here in this ideal, then one of them has to be in this ideal. Yeah. So let I is this. So let fx times gx belongs to I. So it's so which means fx times gx is equal to x times hx. Yeah, then we want to say that either fx belongs to I or gx belongs to I. Yeah. So yeah. So yeah. So one way is to do evaluation. Yeah. So you plug in 0. Yeah, and think of f and g as functions from zx to z. Yeah. So you evaluate it at 0. So f0 times z0 is going to be 0 times h0, which is 0. But z is an integral domain, so that tells you that f0 is 0 or g0 is 0. Yeah, so this will imply, so f, so maybe I should just say what f looks like. So f looks like summation ai x power I equals 0 to n, and gx looks like summation bi x power I equals 0 to m. Then f0 equals 0 tells you that a0 must be 0, and g0 equals sorry, so g0 equals 0 tells you that b0 must be 0. Yeah, and this statement implies that a0 is equal to 0 means you can write fx is x times summation ai x power I minus 1 I equals 1 to n, and similarly gx. Yeah, so this tells you this belongs to I. Okay, so you can directly check that I is a prime, or you could do this quotienting thing as well. So then one would have to prove that gx mod x is z, yeah, which is gx mod x will be actually equal to z. Check gx mod x. Sorry. Gx mod the ideal generated by X is isomorphic to Z. So if you show that, then so this only proves that so this only proves that X is a prime ideal, but it's obviously not maximal because for instance 2 does not belong there, and 2 comma X contains so I belongs to this, and 2 comma X is not the whole ring. Is properly contained in ZX. Okay. So so this also we had seen that it's a proper idea. So somehow by taking combination of these two, you can't get. So if you take any polynomial, any element of this this ideal generated by 2 comma X, then it's called. So we saw that the such an ideal must have constant term E1. Yeah. So this we saw explicit description of this ideal. So this is in an earlier class. So this is F in ZX such that F0 is even. Yeah, so in particular, you can't get so one the unity of this this thing of ZX does not belong to this, so it can't be the whole ring. Okay, so it's not a I is not a maximal ideal. Or if you prove this isomorphism, then it follows that X is a prime ideal because Z is an integral domain, and it's not a maximal ideal because Z is not a field. Yeah. So you can either do it directly, or you can use this. You can prove this isomorphism and use theorems. Yeah. So the abstraction helps. It sort of simplifies things and let you think about it in a more reasonable way. Okay, any questions? Okay, so no questions. Let me go ahead. I hope it's visible. Maybe I'll enlarge it. So this example I've, okay, maybe. So it will be visible. So I'll just make it slightly bigger. And slowly you'll see the bottom line as well. Okay, so the next thing we want to do is show that every non-zero commutative ring with unity contains a maximal ideal. So we know that these rings. By the way, so before we get here, what do you know about this ideal 2 comma X? Is it a maximal ideal?
Yes, sir.
It is a so what is the quotient? ZX. So note that this is isomorphic to Z mod 2, which is a field. Yeah, so you can use I don't know. You can use third isomorphism theorem if you like, or whatever. So I mean, you can directly give a map from this to Z mod 2, ZX to Z mod 2 by sending a polynomial to evaluating it at 0 and going mod 2. Okay. So so you can check that this is this isomorphism hold, and that tells you that 2 comma X is indeed a maximal ideal. Okay, so ZX has a maximal ideal, and so for rings like this, meaning rings which are reasonable, existence of maximal ideal you can prove directly, but but even in arbitrary ring, arbitrary non-zero ring, you can find a maximal ideal. Yeah. So, but for doing it for a completely arbitrary case, you need something called John's lemma, okay, which I'll talk about. So, so for nicer rings, which which are called Noetherian rings in the and these are ZX and QX and these kind of polynomial ring in finitely many variable over fields or integers are examples of those. John's lemma is not needed, meaning you can directly do it, but for more complicated rings like ring of continuous functions over on the interval 0, 1 to R, that's not an example of a nice ring. But that's also a commutative ring with unity, and that also admits a maximal idea. Okay. So, so for abstract commutative ring with unity, which is non-zero, you to show that it contains a maximal ideal, you need something called John's lemma. So, have you seen John's lemma before in your first year in any course?
Yes, sir, we have seen the statement in algebra.
In algebra, so you have seen this statement, yeah, in group theory or maybe in linear algebra. So yeah, maybe for vector. So so anyway, the proof is a bit. So you won't see the proof of this. I mean, maybe you'll see it in topology or something. I don't know. Or maybe not. Because this is more like you can think of it as more like an axiom. Yeah. So so let me first tell you what recall what John's lemma is, and then I'll say a few words about John's lemma, and then we'll use John's lemma to prove things. Okay. So let omega be a non-empty partially ordered set, and this this guy here. The symbol is the ordering. So partially ordered set is so ordering is a relation. Yeah. So a partially ordered set is a relation which is reflexive, antisymmetric, and transitive. Yeah. So so I hope you know what, since you have seen John's lemma, so I hope you know what partially ordered set means. Yeah? So omega is a non-empty partially ordered set. But if you don't know, do let me know. I can explain it in more detail. So maybe I'll just say these words. So partially ordered means this this relation is reflexive. So A is less equal A, antisymmetric. Yeah, antisymmetric, which means A is less equal B and B is less equal A means A equals B. Yeah. So I hope this is antisymmetric. So somehow A less equal B and B less equal A implies A is equal to B. So you can't have A is less equal B and B is less equal A with A and B distinct. That's not possible. Yeah. And transitive. So you know what transitive is. But it's so it in particular means that it's not required that given any two elements omega A and B, they have to be related. So it may be that they are not related at all. So that's allowed. That's what partially means. So assume that so omega less equals is a partially ordered set. Um, um, assume that every chain in omega has an upper bound in omega, then omega has a maximal element. So what is a chain? So chain is a subset of omega, which is totally ordered. Yeah. So maybe I'll just say a chain in omega is a totally ordered subset. Meaning a chain, let's say C in omega is a totally ordered subset. That means I for all AB in C, A is less equal B, or B is less equal. So any two elements of A of C are related. Yeah, so omega may be just partially ordered, but if you are talking about a chain in omega, that means it has to be totally ordered. Okay. So every chain in omega has an upper bound in omega means C has an upper bound. So I'm just trying to explain what the hypotheses are, because we are going to use this lemma, so we know what we should know what the hypotheses are. Yeah. So C has an upper bound means that exists has an upper bound in omega. In omega means there exists m in omega such that for all A in C, A is less equal m. Okay, so then m is an upper bound. Yeah, and C has an upper bound means there exists an m. Okay. So m is an upper bound of C means for all A in C, A is less equal. Okay, and then maximal element, you know what maximal element means. So M is a maximal element of omega means and there is nothing in omega which is bigger than m. Means if A is if m is less equal A for some A in omega implies then maybe since I've started with if, then A equals m. Okay. So this is what it means to say m is a maximal element. So there can't be anything strictly bigger than m. So if something is bigger equal m, then it must be m itself. Yeah. So this is what all the phrases in Zorn's lemma mean. Yeah. So we, as I said, we won't see a proof of Zorn's lemma, but this is equivalent to what is called axiom of choice. Yeah. So Zorn's lemma is equivalent to a bunch of statement in set theory, equivalent to axiom of choice. So so I don't think you'll see this in topology as well, yeah, because I taught topology last time. But hopefully later on, maybe in master's course or somewhere where you do a more rigorous course in set theory or logic, you may see it, yeah. But it's there in many of the textbooks. So what is axiom of choice? So the reason we don't see the proof is because one has to develop an axiomatic way of thinking about set theory and stuff, but it doesn't have any prerequisite, but it requires a bit of maturity to appreciate the proofs. Yeah. So one can do the proofs anytime. As soon, I mean, you can do the proof as soon as you join BMath, but it's a bit abstract and maybe not that necessary at that stage. Yeah. So people, once we understand the concept of what a proof means and things like that, then we would better appreciate the proofs of these kind of. So one should understand a bit of logic and set and what a theory means and axioms, etc. So yeah, so when you join BMath, axioms, etc., axiomatic way of looking at mathematics is still a novelty, right? So first we should understand mathematics in some abstract mathematics in a more reasonable way, and then we do proofs like. So I don't know if you know what axiom of choice is, but I'll tell you this statement, though I'll not tell you why these are equivalent. There are other statements like something called transfinite induction, which is also equivalent to Zorn's lemma and axiom of choice. One more thing. Yeah, so some things maybe in so I don't remember in topology whether I proved some of these equivalences, but I did state it. So in topology maybe you'll see it, but I'll just say what axiom of choice is. So that just for general knowledge. So axiom of choice. So set theory, there are in last century, in the middle of last century, there were many problems with the set. I mean, people realized there are many problems with the way they view sets. Yeah. So many logicians had this paradoxes. Yeah, so to resolve that paradoxes, they started thinking of set theory in a more axiomatic setup. So they have certain axioms which are called Zermelo-Franklin axioms, and there are many other competing things. But let's say ZF, Zermelo-Franklin axioms. So that those axioms are good enough to understand some basics of set theory. But then people realize that there is this choice axiom which the statement which I'm just going to write, and they realize that this can't be proved from ZF. Yeah, and after a while they realize that even its negation can't be proved from ZF. So axiom of choice is somehow doesn't follow from the axioms of the usual axioms of set theory. So they included axiom of choice as an axiom of set theory, and that is called ZFC, Zermelo-Franklin axiom and choice. Yeah, so ZFC is the abbreviation. So most of the mathematicians work on this work assuming that the axiom of choice is true, and so they take axiom of choice as one of their axioms. But there are mathematicians who work there are some very few mathematicians who, mostly logicians, who also work in the setup where the axioms are Zorn's lemma, axioms are Zermelo and Franklin, and negation of axiom of choice. See, the point is negation of axiom of choice cannot be proved using, cannot be disproved or proved using the Zermelo-Franklin axiom. So you can take the negation of axiom of choice as well as your axiom, and there is nothing wrong with it. Yeah? So people use that that theory as well and try to prove something. But that's not most of the mathematicians do. Maybe some logicians do. Yeah. So let me tell you what axiom of choice is. It looks very natural, but some of its implications may not look as natural. So so let I be a set So I'm just stating this axiom of choice. So let I be a set, and E alpha in I be a collection of sets. So it's a collection of sets indexed by I. Then, so this is the conclusion of the axiom of choice. Then there exists a set A such that A contains exactly one element from each A alpha for all alpha in I, for all alpha in I. Okay, so there exists a set. So it's declaring that you can form a set by choosing one element from each alpha. So yeah, since you are choosing one element from each alpha and forming a collection, and you are declaring that is a set. So that's why, since there is a choice involved, so that's why it's called axiom of choice. So it looks natural. So if you are given a collection of set, and then you can of course pick one element from each and form a set. So in fact, I mean, if the indexing set I here is finite, then this axiom can be deduced from ZF, the usual axioms of set theory, but this becomes non-trivial when I is not a finite set. Yeah? So this meaning it can't be deduced when, from ZF when I is an infinite set. Okay, so so this is all I wanted to say about Zorn's lemma and axiom of choice. So we will use Zorn's lemma to prove that every non-zero ring contains a maximal ideal. But before that, maybe we'll take a 5 minutes break, and so we will reconvene at let's say 12. Okay. So let's take a pause and reconvene at 12. Okay, so let's start. So we want to prove this theorem that every non-zero commutative ring with unity R contains a maximal ideal, and we want to use Zorn's lemma to prove this. You know, and we just saw what the statement of Zorn's lemma is. So you want us to make this smaller. Yeah. Okay. Okay, some part of Zorn's lemma is hiding. Okay. So we'll have to move left and right. Oh, it's okay. Oh, yeah, maybe if I do this full screen. Yeah, now it's better. Okay. So let's see a proof of this theorem. So let R be a non-zero commutative ring with unity. We want to show that R contains a maximal ideal. So let's just consider the set omega to be the collection of all proper ideals of R. Yeah. So it contains subsets of R which are proper R ideals. So of course omega is non-empty. So all the hypotheses of Zorn's lemma we will have to verify to apply to get the conclusion of Zorn's lemma. Yeah. So one of the important hypotheses of Zorn's lemma is that omega be a non-empty set. So of course omega is non-empty. Why is it non-empty?
So the zero ideal is there.
The zero, yeah. So the zero ideal is there, yeah, and it is a proper ideal because we are assuming R is a non-zero ring. Yeah, so this requires. So for this This is where the non-zero part comes in. So let's just go up, maybe further up. Yeah. So this guy follows from the fact that R is not equal to 0. R is not the zero ring. Not the zero ring. Yeah, so in particular, this set containing just the zero element is an ideal and is a proper ideal. So omega is non-empty, and of course it is inclusion is a partial ordering. Yeah, so if you take any collection, any subset of power set of omega, inclusion is a partial ordering. Yeah, so it's a partially ordered set by inclusion. So now we'll have to verify the statement that every chain in omega has an upper bound with respect to this inclusion. Yeah. So let I alpha in some indexing set be. So I've used some indexing set so that it becomes lot of easier to write things. So you take any chain in omega, yeah, which I denoted by this collection I alpha in J. So chain is a subset of omega in which every two element is comparable. So either I alpha is contained in I beta or I beta is contained in I alpha for alpha beta in J. That's what chain means. Yeah. When we want to show that this chain has an upper bound. So so here is the candidate for the upper bound. So consider I to be the union of all this I alpha. Yeah. So the claim is I is an upper bound. So which is same as saying that I is a proper R ideal. Yeah. So of course once we prove this claim, then of course it follows that I is an upper bound, because the claim will imply that I is an element of omega, and of course each of these I alpha is contained in I. So it is so that tells you that I alpha is less equals I. Yeah. Okay. So the partial ordering is inclusion. That means I is, so maybe I should have mentioned this a little more with a little more clarity. So I is less equal I prime if I is contained in I prime. Yeah, this is the partial ordering. This is what it means to say omega is partially ordered by inclusion. So now let's prove this claim. So we want to prove that I is a proper R ideal. So first we'll prove I is an ideal of R. So let AB belongs to I. Then since I is a union of these ideals, A belongs to I alpha naught for some alpha naught in J, and B belongs to I beta naughts for some beta naught in J. Yeah. So so what we get is that, but we know that this is totally ordered. It's a chain, so this is totally ordered. So this means that naught is missing. So that tells us that I alpha naught is contained in I beta naught, or I beta naught is contained in I alpha naught. So one of these inclusion will hold because of the total ordering on this thing. Yeah, so that if the first one holds, then of course A and B belongs. If the first one holds, then A and B belongs to I beta naught. Yeah, the bigger one. Otherwise, it belongs to I alpha. So I can just say whichever is bigger, it belongs to there. So AB belongs to one of these two ideals, which means A plus B belongs to one of these two ideals, and R times A also belongs to these two ideals, because if A belongs to one of these two ideals, then R times A for any R in a scalar multiple belongs to these two ideals, one of these two ideals. So if these two elements belongs to one of these two ideals, then of course it belongs to I as well, because I contains both of these ideals. Yeah, so that proves that I is an R ideal. is an okay, maybe an R ideal. So we have shown that I is an R ideal. Now we have to show that I is a proper R ideal. So it's not the whole ring. So if so what does it mean that I is so we'll go by contradiction. So if I is the whole ring, then of course one should belong to I. But if one belongs to I, then one has to belong to I alpha for some alpha in yeah, because I is union of these guys. So if some element belongs to I, it has to belong to one of these one of these constituents, I alpha. Yeah. So it has to belong to one of these guys. But we know that each of these I alpha are proper ideals of and proper R ideals because each of these I alpha belongs to omega. So this contradicts the fact that I alpha belongs to omega because omega is made of proper R ideals, so it cannot contain. So maybe I'll just put this implies I1 belongs to I alpha will imply that I alpha equals R. Which contradicts I alpha belongs to omega. Hence we get that I actually belongs to omega. So that is the claim. I is a proper R ideal. Hence, so and also so what we get is I belongs to omega, and I is an upper bound of this. So by Zorn's lemma, omega has a. So now we can. So now we, if you check, we have verified everything. So omega is a non-empty ordered set that is checked. It's nothing. So maybe that is checked. Then we showed that every chain has an upper bound, and then so now we can apply the conclusion. So the conclusion is omega has a maximal element, and what does maximal element mean? So there is nothing bigger than omega in there. Yeah. So hence by John's lemma, omega has a maximal element, say M. Then M is the maximal ideal of R by definition. Yeah? So that was the definition of one of the equivalent definition of maximal ideals. Yeah? So it has to be maximal among set of all proper ideals of R. And that is what we stated as the definition in last class. Okay. So that proves that that R has a maximal ideal. Okay, any questions? Proper, so there is some question. So anyway, so which was answered from Mohammed. So proper ideal means that it's not the whole ring. Yeah. So so zero, yeah. So proper ideal just means that it's not the whole ring. Yeah. So if you see some question and if there is some doubt, you can one of and that person can't speak out, then you can ask me in the middle, and I'll stop and answer that question. Yeah, so proper ideal precisely means that all ideals which are different from R, the whole ring. So in particular, zero ideal is a proper ideal if the ring is not non-zero. If the ring is zero, then zero ideal is not a proper ideal. Okay. Any other questions? Okay, so if there are no questions, I wanted to define Jacobson radical, but maybe we will we'll do it next time. Okay, so and then make some statement about it. So let's stop here, and if you have some questions, this is a good time to speak out. Any questions from anyone about what we did or today or in the past, or anything about the quiz? Yeah, tell me.
What is J set in the previous theorem?
In the proof, you mean? Yeah. So I just wanted I wanted to take a collection, a subset of omega. Yeah. So and I wanted to index the element of this subset by another set. Yeah. So this is more semantic. So J is just an indexing set. It's an indexing set. So I could have said, just take C to be some subset of omega, which is totally ordered. C is a chain, yeah. But somehow I wanted to index it so that I can write it in a more intuitive way. Okay. So it's just an indexing set, nothing more. Yeah. So I mean I could take J to be same as the C. Yeah, and indexing is by elements itself. So it's just a way to index elements of. Does that make it clear?
Yes.
Okay. Any other question?
Sir,
Yeah.
in last class, there will be an ideal J equal to 5 comma square minus 2 J of X, sorry, Z of X.
Yeah.
Can you explain what you mean by that?
In the last class. Yeah.
Yeah.
So let me actually, since the advantage of online classes is we can go to the last class. Yeah. So let me just.
It's just third example.
Third example. Yeah. Okay. So in ZX, X minus N is a prime ideal. Is this the example you're asking for?
No.
No. Okay. There's some other. This example. ZX mod.
Yeah, there's an ideal J.
Where is the ideal J? This ideal. Yeah. So I and J are these two are ideals. Yeah.
But I'm just asking, what do you mean by J?
So J is the ideal generated by 5 and x square minus 2. So you 5 and x square minus 2 are element of ZX. Yeah.
Yeah, that's okay. But
so you consider the ideal generated by this. So elements of this looks like this is stupid. So elements of this looks like as a set, I'll tell you what it looks like. So it's 5 times fx plus x squared minus 2 times gx by definition. So this is more or less by definition for what ideal generated by these two elements looks like, f and g in ZX. Okay.
Okay.
So this is the set, and this as a set it looks like this, and this is an ideal. Yeah. So it's closed under addition and scalar multiplication. So I is an ideal and J is an ideal and I is contained in this ideal, right? Because what are the elements of I? Is 5 times some fx, where fx is some element of zx. Yeah. So of course, if you take G equals 0, you will see that every element of I is an element of J. So you have that inclusion. So this notation means that the ideal generated by 5 and x squared minus 2. Okay.
Thanks, sir.
Yeah. So examples of elements of this ring is not just x square minus 2, but you can also take x square minus 7 or x square plus 3 and so on. So you just add 5 to it, or you can take you can add 5x to it and so on. Yeah. So there are many. So one should play around and see what are the elements you will get in this idea. So so this is an abstract, I mean, this is a way of denoting it, but one should know what are the actual. So, look at some examples so that it gives you a feel of what elements are in this ideal and so on. Okay. Any other question? Okay, so if there are no questions, maybe we'll stop now. Okay, so if you have some questions, this question suggests that ideals are very new to you, and maybe maybe we should have done a little more examples of ideals. But if you, so maybe I'll use the Google Classroom platform to discuss a little more about ideals. Yeah, so if you, I'll try to ask post some questions about ideals and stuff, so that may help in understanding it. Okay, so let's so that's it for now. So I'll see you guys tomorrow. Okay, bye bye.